Yeah, thanks. So, welcome to Compression Carcinized, implementing zlib-rs. So, about that name, it alliterates, which is why I picked it. But this word, carcinization, comes from biology, and it means to evolve a crab-like body plan, which is a phrase I really quite enjoy. And we'll see what we can do with this idea a little bit later, but this happened several times over the course of evolution because it turns out that being a crab is an incredibly successful survival strategy. So, what is zlib-rs? Well, as the name sort of implies, it is a Rust implementation of a thing called zlib. And zlib is a library for compression, in particular for dealing with the gzip compression format. And it is a very widely used format, and therefore zlib is used in a lot of places. So for instance, if you download a binary on the internet, like RustAnalyzer, it is very likely that these are provided as gzip files, both because the compression is pretty good, and because most users already have some kind of program on their device to decode such files, right? So there are definitely better compression methods out there today, but a lot of software is just compatible with gzip. Even if you haven't downloaded RustAnalyzer today, you've likely loaded a web page like rustlang.org. And it's very likely that those web pages also use the gzip encoding and therefore indirectly use zlib to encode that page. So when you load a page, you don't get raw HTML bytes, but instead you get sort of a compressed representation, and it gets decompressed on your local device. So zlib is used in a lot of places, and it's really at the foundation of a lot of our tech stacks, in particular of a lot of internet infrastructure. And so it's a very important project. To get a bit of a sort of a better idea of what zlib is that in practice it is often a dynamic library that is somewhere on your system at least once. So here I've tracked it down on my own machine, and we can see that it exposes a bunch of functions that have something to do with compression or uncompression in their terminology. And so applications on your system can load this library in and then make use of this compression and decompression functionality. In practice, this is a C dynamic library, which means that it exposes functions like this, which looks very nasty from a Rust perspective. It has like pointers, mutable pointers. It returns errors, but really it's an int because, of course, right, C types. It can do better than that. We can. Sort of that as sort of a summary of that. So the idea of the zlib-rs project is actually to sort of aim high and replace that C dynamic library, to build something in Rust that pretends to be that C dynamic library, but secretly it's all, nice Rust inside. So that also means that our sort of target audience is people that don't necessarily have sort of warm, fuzzy feelings towards Rust. And so we need to somehow tempt them to upgrade, right? To sort of make that very easy. And we can do that not by sort of re-implementing all of the logic in Rust and then saying like, hey, we made this really cool Rust library, but by actually sort of bringing it to them so that upgrading to zlib-rs would be just swapping out a file. But of course, like if we go through all the trouble of implementing that logic in Rust, we may as well also, provide it on crates.io and sort of make it available to the Rust ecosystem. That still has advantages if you're using Rust anyway, then sort of importing it directly into your Rust compilation is better in various ways than relying on it as a dynamic library using that very nasty C API. So today we're going to go over sort of a crash course in compression. Sort of how does zlib work, what does it do, and sort of why is it effective? Then having a look at the zlib ecosystem, because when you are going to like rewrite it in Rust, it's important to know what you're actually rewriting so that you can sort of look at design decisions and make choices. Maybe you want to adopt certain decisions, maybe you want to innovate in certain ways. And so it's a good way to have a bit of an overview of what that ecosystem looks like, what properties you want to preserve. And finally, some ponderings on porting, on sort of this project of like rewriting the bottom of the stack in safe Rust, which to me is really like delivering on the original promise of Rust, sort of bringing that improved language and toolchain to all of those places. Let's see what we can learn and what we can maybe do better. So the sort of core idea of compression is, why use many bytes when few do trick? Right? Storage space and bandwidth are expensive, and so we would rather send fewer bytes than many bytes. Also, especially in the context of the internet, sending fewer bytes over a wire is faster than sending many bytes over that wire. Now, this is slightly more complicated because compression and decompression are not free, and so you need to somehow make sure that the compression, then sending fewer bytes, and decompression is faster than sending the uncompressed stream. But in practice, gzip is sort of used everywhere on the internet, so clearly that must work. But that is something to keep in mind. Performance actually really matters here. So the kind of compression that we're looking at is so-called lossless compression. Compression where if you have some data, you compress it, you decompress it, then you want the original sort of input back out. This is sort of opposed to lossy compression, where they can get away with chucking out detail, like in JPEG images or MP3s. We don't get to do that. We need to actually be able to replicate the original input, and so we can't just conveniently forget information. So the algorithm that is implemented here in zlib is one that looks at your input, which is in general a byte stream, but because we're humans, we're going to use characters today. And it's going to look for repeating sequences of characters in this input. So here we have the string foo bar foo, foo repeats, and so what this algorithm does is it replaces this sequence with an offset length pair. And so what happens here really is that this offset length pair refers to an earlier part of the input string. And this is more worth it, this saves more bytes when that repetition is longer. So if we had 4 characters instead of 3, we would gain basically by having fewer bytes to transmit at the end. This is also a representation that is fast to decode again, right? So this is relatively straightforward to like almost interpret. It really looks like an interpreter loop when we start decoding this information. The tricky bit is finding how to insert these offset length pairs, right? If you look at this sort of seemingly arbitrary sequence of characters and ask you like, okay, what offset length pairs do I insert? What are the repetitions that you see? That is hard. And that is hard for humans, but also for computers. Like if we throw a bunch of nested for loops at this, performance would just be absolutely terrible, right? The big O of that would be bad. And so we need to be smarter than that. We need a couple of tricks to sort of break down this problem and make it manageable. Because again, like we need this to work on web pages on the internet. Like sort of throughput and time to first render are really important. Yeah, and an additional problem is you want to not just find repetitions, like finding one character repetitions is easy, but they need to be as long as possible because that gives you the best compression. So in practice, how zlib works is it runs over your input, and so we have a sort of current position, a current character, and we're going to search backwards for repetitions that match with the current cursor position and the sort of characters following it. Right, so we run over our data, character by character, but then we need to sort of impose some restrictions on this to make it manageable, to get that big O complexity down. And basically this revolves around reducing the amount of work that we do per character. And so the first limitation that we're going to impose is that we're going to only look within a certain amount of space backwards. If it's sort of off to this side, it doesn't count anymore. We can't use it anymore. And so this makes our search space smaller, but also it reduces the likelihood that we'll find a good match within this smaller window. And if we make it larger, then the chances are better, but we spent more time searching through. And because there is no sort of objectively good answer to how big that window should be, it is a user configurable parameter. Similarly, the compression level is another user tunable parameter, and this is roughly a measure for how hard we're going to try to find the longest, the sort of optimal match in our window. So here, if we search our window from left to right, we find a 3-character match, and we have to sort of decide, are we going to continue to search to find a 4, 5, potentially, a 100-character match, or are we going to just stop here and not waste any more time and move on to the next character of the input? And so again, there's no real, that's a gamble. You just don't really know. But at a low compression level, you basically say stop when you find something halfway decent. At a high compression level, you would continue to search, sort of hoping for sort of getting lucky. That still wouldn't really work, though. If you go about it in this way and you search through this whole window linearly for every character, this window is typically 32K or 64K. That will be way too much work that you do per character of the input. And so actually what we need to be doing is remembering some of that work. And so what we're going to do, what the zlib algorithm does, is it keeps track of substrings of the input, 3-character substrings, and the indices at which it has found these substrings. And so in this case, we find the string FOO at index 0. We find OOB at index 1, and so on, until we find our second F. Because in this case, we're again we want to insert the string FOO, but it's already there. And so now we know two things, which is that at index 0, which is in the value set of foo, we find a match of at least 3, which is already pretty good. That's about break even in terms of do we gain anything with that insertion of an offset length pair. But potentially the match is longer, right? That is what we're hoping for. But also any index that isn't in that set, we know for sure that there won't be a match there. Like OOB will definitely not match FOO. And we don't need to actually go look at the data and compare that character for character, but we know because of this dictionary that we've kept that we don't even need to go look there. And so in this way, we can skip over vast amounts of the input and just never treat them at all. So I hope that sketches roughly how the algorithm works and gives some intuition for why this is so incredibly effective on web data. Because if you think about HTML or CSS, there's just so much repetition in there, the repeating class names, property names, just words in text, that even at low levels of compression, you achieve very good results. And at low levels of compression, you expend little time, but you still get actually quite a sizable reduction in the overall payload. There's one further trick that zlib uses, which is that it is a streaming implementation of these algorithms. So that means that if you load rustlang.org, you don't just wait for that whole compressed HTML page to arrive and then decompress it, but instead your device can start decompression as soon as the first byte comes in. And so this really helps us overall that time to first render. Unfortunately for me, it also really complicates the implementation. Because now you need to be dealing with you get 1 byte of input, you get 300 megabytes of input, you get 3 bytes again. And so you need to keep track of this, and we make heavy use of fuzzing to make sure that the implementation is robust for this fragmented input. All right, so that's roughly what the algorithm does, and I hope that is useful. So what are we actually implementing, though? Well, so generally, when we talk about zlib, the zlib that is actually everywhere because it is a default in a lot of operating system distributions. This thing is called zlib-adler, the OG, and its goal is stability. This is a dependency from 1995. If you look at its source code, you can really see that. It still supports 16-bit systems. Who here has programmed on a 16-bit system? Exactly. And also it doesn't use modern hardware very well, right? So it's one generic implementation that runs everywhere. It is good C code in terms of performance. Aesthetically, I have thoughts, but and so it doesn't use a lot of modern hardware instructions in specific ways. And this is unfortunate because that is where most of the innovation in the hardware space has been for at least the past decade. We can't run more instructions per second anymore, and so what we're doing is inventing more powerful instructions that do more effective work in a single instruction. And to some extent, compilers can transform our standard programs into programs that use these instructions, but generally they just aren't capable enough. And you need humans, for the time being, to actually write those implementations. So because performance is important to many organizations, several forks have been made of zlib-adler. The most prominent of these is zlib-ng, where basically they say, we want performance. We want performance specifically on modern hardware. So that means removing a lot of legacy stuff, amongst other things, the 16-bit support, and relying on these modern instruction sets that have these SIMD instructions that do that more work per instruction. But zlib-ng is still fully API compatible, so that means it exposes all of the same names, with all of the same type signatures as the original zlib, and so it is a drop-in replacement for the original zlib, just with less platforms that it supports, but still the same API. Now, these are both C dependencies, and C has various problems. Rust has various solutions, so all of the usual points apply. We have bounce checking, we have borrow checking. Rust is nice to write. I think for a project at this level of the stack, it is especially important that we vastly reduce the surface area of our project. So in part, this is reducing the amount of code that we write through good use of the standard library. We have one dependency, which is zlib-rs, which I would like to get rid of. We'll get there. In part, though, it is actually using cargo, because it is, I'm going to posit something here. It's my opinion that any sufficiently complicated C project contains an ad hoc, informally specified, bug-ridden, slow implementation of half of cargo. This implementation right. You should, like, just sort of like looking at, an accident, you should look at the build system of some C projects, because in practice, this implementation of cargo is a makefile and 1,000 lines of bash. No one wants to write that. No one wants to read that. Detecting errors in that kind of code is incredibly tricky. And this is not hypothetical. This is sort of part, at least, of the recent XZ attack on another compression format, where a malicious maintainer added a single character to one of these bash scripts, and it made the script take a different branch, and then you are now, compromised. Update your threat model. Don't use thousands of lines of bash. So if we want to do better than that, in Rust, the way to sort of use or interact with gzip files, the recommended way, is Flate2. And this is a crate that provides a nicer API for zlib and similar functionality. So instead of that nasty pointer-based thing, we actually get impl read, impl write, we return results, etc. It's very nice. It's also used in cargo, because again, gzip is everywhere. But Flate2 itself is actually just a shell. It doesn't implement any of the actual compression logic. For that, it uses one of several backend crates, which you can sort of toggle with a feature flag. So you can use zlib-og if you really want the compatibility, or you want to just use the thing that's already on your system. You can use zlib-ng if that is what you want. But also, you can use Rust implementations. And until recently, the only Rust implementation available was mini-zoxide. And this is a safe implementation of a subset of the zlib API. So it really covers a lot of use cases for Rust users, but it leaves some things to be desired. So it doesn't cover the full zlib API. It's not a drop-in replacement. And also, it is relatively slow because it doesn't make sort of dedicated use of these SIMD instructions. And zlib-rs fixes this, right? We still want safety in the sense that we implement this in Rust. We try to be really careful, but also we really want performance. In order for this implementation to be competitive, we need the performance to be at least okay, and then hopefully over time better than the alternatives. We also, implement the full API. So in practice, this sort of architecture that we get is this unsafe sandwich, which, doesn't get food poisoning, but there's some stuff in there that we'd rather like, So at the very top, we need an unsafe API for exposing with the outside world. That is that nasty pointer-based API that we need to provide. That's sort of the point. At the very bottom, we have SIMD and even some inline assembly to achieve the performance that we want. And these are sort of like, we can't get around the unsafety here, probably ever. And then in the middle, we have mostly safe business logic. There's some unsafe in there dealing with uninitialized memory, but those are actually, the code comes from the standard library. It's just not stable. And so over time, we can hopefully get rid of that. So then, like in terms of performance, this is sort of what the landscape looks like. This is speed up versus zlib-og, sort of as a factor of its speed. First of all, zlib-og performs not well. Then mini-zoxide really tries, and at low compression levels, it's doing all right. But at higher compression levels, you can really see the difference between implementations that use and those that don't use the explicit SIMD. And in general, that's like almost a 2x difference there at level 6, which is the default. Right? And like higher compression levels basically do more computation, so the effect of using SIMD becomes more pronounced. Also, like, we're doing all right with zlib-rs, but it's still not quite there with zlib-ng. That just means I get to stare at assembly for many more hours. So you can actually use this today if you're already using Flate2. We've been a little bit quiet about it, but the implementation totally works, so you can flip this feature flag. Please give that a go if you're already using Flate2 and let us know how it went, both if it went well and if it went poorly. All right. So finally, I wanted to say some stuff about sort of this project of translating C into Rust, because rewriting in Rust is easy to say, and the people who say it most rarely do the actual work. You know, typical. So something I've been thinking about is this sort of spectrum of porting, this sort of idea of we can have an organic implementation or a line-by-line rewrite of an existing C project. And there's various places on this spectrum with various trade-offs that we can make. So if we have a sort of fresh implementation, like Brussels or NTPDRS, then they, in a sense, reinvent the wheel. They sort of throw out a lot of existing knowledge and code and start from scratch and have to sort of absorb and digest all of the information relevant to the domain. On the other hand, they can also innovate in terms of mostly architecture, I think is the most useful one, by sort of being unconstrained by existing implementations. Refactoring architecture is really hard in practice. So in a sense, this is high risk, high reward. It takes a long time for you to digest all of that information and build an implementation that works, then making sure the performance is sort of okay, because that matters at this level of the stack. But ultimately, you get a sort of very nice payoff in sort of the best Rust solution that you could probably come up with. On the other end of the spectrum, we have line-by-line rewrites. And in the most extreme case, we could even do a mechanical rewrite using a tool like C2Rust. And the Revit project is an example of such a project. So this translates David, which is an AV1 video format decoder, into Revit. And so what happens here is that you reuse a lot of that existing knowledge, right? As you can imagine, video decoding, not an easy topic. So you reuse a lot of knowledge about how that domain works and also the sort of performance engineering that went into making that implementation efficient. You also inherit the architecture. It really depends on what C code base you start with, whether that is a problem or not. But ultimately, what you get is something that works on day one. It compiles with a Rust compiler on day one. It has the same behavior and performance as the C implementation. You can test and fuzz it to sort of make sure that you never break sort of those correctness properties. Most of your work, though, is cleaning up code that looks like this. This isn't even the worst of it, but there's a lot of this code. It's very sort of verbose, but its input was C, so what did you expect? And so while this is sort of annoying, I also think that everyone here can see some improvements that they'd make to this code. And so in practice, cleaning this up is mostly a sort of a pretty zen process of moving characters around, turning while loops into for loops, etc. It's only occasionally that you step on a borrow checker landmine, and you have to sort of take a step back and reconsider, like, okay, is the architecture, does it actually work? Do we need to rethink something? Are we going to use some unsafe code here? Choices. So in practice, this is something that Revit has to battle quite a bit because the original library uses threading. And so, you can imagine how that would be, not a great time. Zlib is somewhere over here, sort of off to the right, where I did most of the translation by hand from the C of zlib-ng. This is actually a pretty straightforward process. It just takes some, editor skills. And we reuse a lot of that existing knowledge, both in terms of correctness and performance. We get very quick results, like in a week or two, you can actually have something that is very solid. And our architecture was constrained anyway, so we didn't think we could really innovate there. If we have that C API we need to expose, we need to sort of implement that streaming that really constrains what you can actually do. So, rewrite it in Rust and you. If you've seen the sort of marketing recently and also the Rust talk yesterday, I think what we're sort of realizing is that actually we need to be compatible with existing implementation. So instead of like sitting on our high horse and saying like our Rust implementation is better than yours, we actually need to sort of bring it to the places where the software is actually used in order to achieve any real world impact, which ultimately like that is what I care about. I want my work to sort of be the foundation for modern digital infrastructure. And so we're working on all of these compatibility layers and making integration with existing systems easier. That is why zlib is a drop-in replacement. Also, we have to be just better, because for someone to mess with their existing configuration on some obscure server that they haven't touched in 10 years, it takes a lot for them to upgrade to our version of X, right? That is just not an easy process, not really something you want to deal with, and it's never urgent until it is. So we actually try to just add more functionality, add better error messages. NTPD is a better algorithm. Brussels is actually a better and faster implementation of TLS, and we have to be better in order to get any uptake in the sort of broader community. And then sort of, I don't know, more complicated things. Funding is always a problem for this kind of work. It is, again, very important, but never urgent. It's not very flashy is another problem of these projects, right? Like what TLS implementation you use is never relevant for your customers until it is. And so it's never urgent to upgrade. But the funding has actually vastly improved versus a couple of years ago. Memory safety is a much more active topic in conversation. A lot of engineers are really sort of on board with this, and it just takes people to get over that hump of sort of actually doing the upgrade process, looking up the config file, translating it over to the new thing, and actually using this stuff in production. So if you are in a position to sort of smuggle in some unglamorous Rust into the bottom of your stack, please do. And please let us know, because it really makes our day, and it really makes this sort of project of using Rust at the very foundation of our systems that much more possible. All right, so in summary, why use many bytes when few do trick? Compression is very neat and very useful and used everywhere. In particular, on the web, it is unreasonably effective due to the type of content that we set. If you are already using zlib-rs, or if you are already using Flake2, please try out zlib-rs. Let us know how it went, right? Please use more unglamorous Rust in production. It doesn't need to be worthy of a blog post, like just actually use Russells instead of OpenSSL. And finally, keep evolving crap-like body plans. Thanks.
All right. Are there any questions?
I have heard, by the way, from some people that we would like the question askers to stand up so that the camera person can find them.
Hi, which levels of SIMD do you support? Do you only do AVX, AVX2, 512?
So in the current sort of, like, we're not entirely done with this. So generally, we want to support everything that x86 has. So that would be like SSE, the various versions of SSE, and then AVX and AVX 512. And also in ARM, we support Neon currently. And then, I don't know, there's some ideas about, do we want to do RISC-V or do we want to do other things? This is sort of needs-based and also based on what hardware I have. So like I don't have AVX 512 in my CPU, and then actually implementing that is tricky. So we'll get there and sort of roll out support. But this is really the easy part, at least if we can sort of adopt that code from zlib-ng. Also, PR's welcome, I guess. You know, if you really like looking at SIMD code, it's kind of rough.
Not bad. Hello. So I had a question about error handling. So you mentioned that the C API has just uses instance stuff, but you also support that API.
Yes.
So internally, are you able to use nicer Rust errors and then expose those back as the C API, or how are you managing that?
Well, sort of part of what the C API means is that error handling isn't that present in the code that we translated, right? So it also just internally returns an integer and potentially sets a character pointer to a static string indicating roughly what went wrong. So certainly what we aim to do is add more error messages, because there are many cases where the computer just sort of says no. You get a sec fault and it's not clear why, and you just configured something wrong, and the system should be able to handle that. So we can definitely improve there, even for C API users. And then what we didn't really talk about, but like our Rust API is not ready. I think even then the goal would be to use Flake2 as the actual interface to the implementation. But right now what we use is basically the C API for interacting between Flake2 and it's called libc rs sys, because it exposes a C API, even though all the implementations are actually in Rust.
Anything else? I see some here.
Hello, back to the topic of SIMD instructions. How do you do dispatch for different instruction types for different x86 processors, for example?
You mean the difference, like, yeah, okay. So there is a macro in the RustNL library, which will, it's something like, is x86 feature detected? And you can query that at runtime. It will resolve to something, if at compile time, you know you're going to definitely have a certain instruction set available. It will hard code that. It will just be like true. Otherwise, it will query at runtime and then cache what instructions your CPU actually supports. This is very important, mostly for safety of that bottom sort of thing, right? Like SIMD operations in general do like 8 additions in one go. So that is not unsafe. The unsafety is computers really hate it when you make them execute instructions they don't know. And so these instructions are not always available, and we need to actively check, and this is part of the unsafe contract. So there is support in the Rust standard library for that, and we plan to use feature flags for if we want to like compile with no standard. So you have to explicitly toggle on, like, even though I am on some embedded device, I still want AVX2 optimizations.
Okay, more questions. Oh, yeah. The microphone's going all the way across.
So how many bugs did you find in the original implementation just by porting to Rust?
So this is funny, right? So zlib-ng is used incredibly widely, and what if, like, the way I think about it, it gets fussed in production billions of times a day. And so in practice, finding correctness bugs with this sort of general settings, generally accepted settings, I don't think you're actually really going to find much, because any input that could have been thrown at that algorithm over the past 30 years, sort of like they would have found the edge cases. It's much more around usability, that if you configure something slightly wrong, it will just like segfault your program, which is acceptable in C, I guess. Like, don't do that, but like we can do better. So it's mostly around usability, not so much correctness of the algorithm. That's been hammered out long ago.
Okay, great. I see another question over there.
Yes, so that answer kind of makes me think of another thing, which is like, if you're building foundational libraries in Rust, you know, how do you think of the strategy to encourage the adoption of those libraries more widely than just in, say, Rust projects, right? So that they get more widely used, more widely tested, you know, become part of the larger, say, you know, open source ecosystem used by many languages and operating systems.
Right. So this is sort of a like one step at a time process where one by one we talk directly to an engineer at organization X, and they smuggle in some of that Rust code to the bottom of the stack. We try to make it really easy, right, by making this a drop-in replacement. Russell's is now working on OpenSSL compatible APIs. And then otherwise, it's also a matter of like if you look up the documentation of zlib, it shows that it's from 1995, right? We can do better than that. We can have a proper tutorial sort of explaining the general concepts and have proper API docs. So it's mostly about helping actual developers sort of make that process very easy, because it is scary. It is sort of a risk that you take in the short term, hopefully preventing major catastrophe in the long term.
There was another question over there, I think. On the standing row there. There we go.
Hi, thank you for the talk. So I think you mentioned somewhere, and correct me if I'm wrong, using fuzzing to check if the implementation was robust. Do you remember correctly?
Yeah.
So which crates and tools did you use for fuzzing?
This is just a standard cargo fuzz, which is unfortunately still nightly, so you have to rebuild the whole thing. But like just cargo fuzz, and then we have to be a little bit, and I think we can still be smarter about this, like what input you actually feed it, because you can give it a random sequence of bytes and it works well and that needs to work, but it's usually not that interesting. And also especially for decompression, we also try to give it invalid input to just sort of make sure that it doesn't do anything weird, like run into a loop or a panic or something like that. And like, yeah, you just let that run for a couple hours, and then if it comes back good, then, you know, you have increased confidence.
Yeah, makes sense. Thank you.
I mean, there's lots of testing in general of the library too, based on tests from the C code, but also because we did sort of write it piecemeal, we have tests in the individual modules testing smaller bits of logic, because the only tests that the original C project has is end-to-end tests. And that is fine if the end-to-end thing works, but if you have a bug somewhere in the middle, then it's really hard to track down why that is exactly. I would argue our implementation is better tested.
All right. One final question over here.
Do you also focus on the C development experience so that C developers can directly use your project instead of using zlib-ng or other conf generation stuff and like zlib provides on most platforms.
So this would be in a scenario where you would want to like statically compile this in? Right. Okay. So that's not really something we've considered. I'm not familiar enough with the sort of like how people use zlib in a static context for whether that makes sense to us. If you're using C anyway, maybe you want to just continue using C. But we can definitely invest some time in also making that experience easier. So I do think it really helps that we have sort of Rust doc where we also sort of need to annotate all of these sort of unsafety assumptions that we make. We occasionally need to make slightly stronger assumptions about like these two pointers should not alias because otherwise things will sort of go sideways. And so also just that documentation in general will be helpful, I think. And also we can just make a better introduction to the zlib API than that webpage from, perhaps before my birth. Yeah. I mean, we're happy to help out also for those use cases.
All right. Thank you so much. Please give a big hand to Folkert.